Process Safety, Module 3, Reaction Calorimetry, by Denis Pratt, Sanofi. This last module on process safety will help you to understand basic calorimetric experiments, read a thermogram, learn the fundamental calorimetric formulae, and identify thermal hazards. If you have not yet seen the first two modules on process safety, please begin with that. The first module is dedicated to safety in screening experiments with notions of hazard and risk, the hazards links with materials or operations, the hazardous chemical groups, and a short presentation of differential scanning calorimetry. The second module is dedicated to scale-up, mainly in kilolab and pilot plant. How to conduct a safe scale-up, the explosive atmospheres, the main process hazards, the ranking of reaction hazard, and the risk analysis. Calorimetric experiments aim at determining the safe way to conduct the desired reaction and to avoid the undesired events. The main process hazards are the runaway, when the reaction is no more under control and the reaction mixture starts to decompose. A runaway is very energetic, circa 10 times more than an exothermic reaction. Runaways are rare, but may be catastrophic. The overpressure has two origins. Either the reaction is endothermic but forms gases in an uncontrolled manner, such as the formation of an acyl chloride with thionyl chloride, which give SO2 and HCl. Or the reaction is so exothermic and sudden that the solvent overboils, like when a Grignard reagent is formed. In order to avoid the pneumatic explosion of the reactor, it is equipped with a bursting disc or a safety relief valve, and the vent is directed to a catch tank. The decomposition on drying, and the solvent fire, which requires prevention measures such as inertization, ventilation, ATEX zoning, etc. Three main categories of safety studies are conducted with specific purposes. First of all, we wish to know the safety limits, so we need to identify at which temperature the decomposition starts and if it is sudden and energetic. This is done by differential scanning calorimetry, as explained in Module 1. Secondly, we wish to have all calorimetric data on the desired reaction. This is done by reaction calorimetry, often in isotherm mode. The heat flow and energy of the reaction are measured, as well as the gas evolution. Other data are calculated, such as the maximum temperature reached under adiabatic conditions, which is important to rank the reaction hazard. The explosion of dust clouds may be catastrophic, like in Blaye near Bordeaux in 1997. Specific studies are conducted, especially if the product is milled or grinded. One measures the self-decomposition properties by DSC and the ability to ignite in air by specific techniques I will not detail here. A reaction calorimeter is essentially a reactor, which can also be used for process optimization. In the reaction calorimeter, we reproduce the operating procedure which we plan to scale up. After the reaction is completed and the thermal data recorded, it is important to isolate the product which has been obtained to make sure that the reaction worked as planned. The calorimeter continuously measures the heat flow and calculates the total reaction energy. It also calculates the mixture specific heat, and from this data, the maximum adiabatic increase in temperature, delta T adia, in degrees. We describe here the RC1E calorimeter of Mettler based on the measure of the temperature difference between the reaction mixture and the double jacket fluid, but there are many different technologies. In a calorimeter, all heat flows equilibrate and the system is designed to limit the thermal losses. The most important term for us is Q reaction. This is what we wish to measure. The second most important term is Q flow, the heat exchange through the vessel wall to the jacket fluid. If the reactant which is dosed is colder than the reaction mixture, some of the reaction heat is absorbed by the reactant, termed Q dose. If the reaction is run at reflux, The heat is evacuated by the condenser, termed Q reflux. The losses, termed Q loss, are limited to the lid. A small amount of heat is accumulated by the system and another is given by the storer. Generally, the last three terms can either be estimated during the calibration or can be neglected. Also, the term Q reflux is eliminated if there is no reflux. So in the end, it is quite simple. Q reaction is equal to minus Q flow minus Q dose. The basic equation to remember all your life is Q flow equals to UA T reaction minus T jacket. U is the exchange coefficient in kilowatt per Kelvin per square meter. A is the exchange area between the mixture and the jacket in square meter. This is a fundamental equation in calorimetry. I give you a simple example. How to heat a house at the lowest cost? We wish to reduce the losses, that is to say, to reduce Q flow. First of all, by an efficient insulation, you reduce U, the exchange coefficient. Secondly, you can imagine that the house on the right will be warmer than the house on the left. For the same volume, the area is lower. Thirdly, do not heat at 25 degrees. 19 degrees inside is sufficient. Contrary to a house, in a reaction vessel, we try to favor the heat exchange in order to cool down exothermic reactions. But unfortunately, this is not easy on large scale. For glass-lined reactors, U is low. Besides, the ratio area on volume is lower for big reactors. Also, we cannot cool down as rapidly as we wish. The cooling system limits the flow rate and the temperature of the jacket. The term Q dose is not often very high. M is the mass of the solution dosed, Cp is its heat capacity in kJ per kilogram per Kelvin, and T is the dosing time in seconds. If the reagent is at a lower temperature than the reaction mixture, part of the reaction heat is absorbed by the reagent. In the end, the equation is in kilowatt, Q reaction equals to minus UA T reaction minus T jacket minus MCP T reaction minus T dose divided by the time. This is the green curve here for a hydrolysis of thionyl chloride in sodium hydroxide in excess. As you can see, the red curve TR minus TG is very close. This is the main contribution. Integration of heat flow with respect of time gives the reaction energy in kilojoule. The blue curve represents the dosing. There is almost no accumulation. The heat flow drops rapidly after the end of the dosing. Usually, the energy is expressed by mole of limiting reagent, here 400 kJ per mole of thionyl chloride. By convention, exothermic reactions are expressed with a negative energy because the heat is dissipated outside. But I don't like it at all because this negative energy corresponds to a temperature increase. Here, delta T adia is equal to plus 39 Kelvin. Do not forget to specify the sign for the delta T adia. The reaction energy delta H in kJ per mole gives an idea of the reaction hazard, but not of the process hazard. Delta T adia is more useful. It represents the increase in temperature in case of rapid introduction of the reagent solution, together with a cooling failure under adiabatic conditions. The maximum heat flow is an important figure too. An industrial reactor cannot eliminate more than 100 watts per kilogram. The second fundamental equation you need to remember is delta T adia equals to minus delta H divided by MCP. Delta H is the total energy dissipated in kilojoule. M is the reaction mass at the end of the dosing in kilogram. Cp is the heat capacity of the mixture in kilojoule per kilogram and per Kelvin. This equation shows that an exothermic reaction can easily be managed by dilution. If you double the mass, you divide the temperature delta T by 2. The specific heat is obtained by calibration. It reflects the capacity to absorb heat. Water has the highest Cp, 4.2 kJ per kilogram and Kelvin. The chlorinated solvents have the lowest CP, chloroform 0.9, dichloromethane 1.2. This is another good reason to avoid chlorinated solvents. Note that sulfuric acid also has a low CP. Most organic solvents have a CP between 1.7 and 2.7 kJ per kilogram and per Kelvin. The shape of the calorimetric curves also show if a reaction is instantaneous or not, if there is an induction period. If you mix all reactants, reagents, and solvent and heat up the mixture, the curve will indicate at which temperature the reaction actually starts. And the calorimeter will calculate the accumulation at the end of dosing, that is to say, the thermal completion. As explained in Module 2, the calorimetric experiment gives a good approximation of delta T ADIA, and thus of MTSR, the maximum temperature of the studied reaction. By comparison of MTSR with the boiling point of the reaction mixture and the temperature of decomposition, most often obtained by DSC, we are able to rank the reaction according to 5 classes of criticality. 1 and 2, reaction thermally safe. 3, risk of overebullition. 4, risk of overebullition and possibly decomposition. 5, risk of uncontrolled decomposition. In conclusion, reaction calorimetry permits us to follow the heat evolution of the desired reaction. The reaction is carried out under normal conditions. The calorimeter measures or calculates the reaction energy, the maximum heat flow, the heat capacity of the mixture, and the maximum increase in temperature. It detects the induction and accumulation phenomena, and it allows a process safety ranking. Besides, a reaction calorimetry experiment helps the process optimization. It permits to establish the most effective temperature reaction without induction, to calculate the safe dilution and the safe dosing time, and to check if the heat flow is compatible with the cooling capacity of the industrial reactor.